Dissolved oxygen, or DO, is the amount of free gaseous oxygen present in a body of water. Oxygen from air is directly absorbed by direct diffusion and agitation of the water's surface by wind action and turbulences in the water. The amount of dissolved oxygen present in water depends on various factors such as surface area of the water exposed to air, temperature of the water body, salinity of the water, pressure changes, level of organic activities present within the water body such as photosynthesis, respiration, decomposition, etc. Dissolved oxygen is usually measured in milligrams of oxygen per liter of water or percentage of air saturation. It may also be reported in parts per million or ppm. 1 mg per liter equals 1 part per million of dissolved oxygen. DO values can range from as low as 1 mg per liter to as high as 20 mg per liter. Value extremes can be lethal to aquatic organisms, especially fishes. Water with a DO value of between 5 to 8 mg per liter is generally considered healthy water. Values below 5 mg begin to put the organisms in the water under stress. A water body with DO values less than 2 mg is called hypoxic water and cannot sustain life. Mass fish kills is an important consequence of low DO values. Eutrophication or excessive algal and plant growth also results in extremely low DO values. There are different ways of measuring dissolved oxygen in a sample of water: colorimetric methods, sensor methods, and titrometric methods. In this video, we'll be discussing in detail and demonstrating the Ulsterberg modified Winkler's method for DO estimation, since it's the most routinely employed method for DO estimation. In addition, we'll also discuss briefly about the conventional Winkler's method along with the Riedel-Stewart modified Winkler's method. The main reason why the modified Winkler's azide method is more widely accepted and used is because interferences from nitrites is a common problem encountered during DO estimation of surface water samples. The traditional Winkler's method can be used only for estimating dissolved oxygen content in clean waters of lakes and streams, which are known to be free from iron, nitrites, or organic matter. In the modified Winkler's method, the nitrites are destroyed by the addition of sodium azide, as shown in the following reaction. The traditional Winkler's method for estimation of dissolved oxygen in water was originally developed by a Hungarian chemist named Lajos Winkler in 1888. The Winkler's method is an iodometric titration method and is based on the quantitative oxidation of iodide ions to iodine by the dissolved oxygen present in the water sample. Subsequent titration of the iodine generated using a standard thiosulfate solution reveals the amount of oxygen present, which is computed on the basis that 1 mole of oxygen reacts with 4 moles of thiosulfate. The stoichiometric equation for the reactions involved in the Winkler's method is as shown. In the first reaction, the Mn2+, which is added to the water sample in the form of manganese sulfate in the presence of oxygen, is oxidized to Mn4+, which precipitates as a brown-colored manganic hydroxide. In the second reaction, the brown hydroxide precipitate is dissolved by the addition of concentrated sulfuric acid to again form manganese sulfate. Under the influence of this low pH condition, the manganic hydroxide oxidizes the iodide ions to free iodine. In the third and final reaction, which takes place during the titration of the free iodine with sodium thiosulfate, the thiosulfate ions reduce the free iodine to iodide ions. The amount of iodine present at this stage is directly related to the amount of oxygen present in the water sample. 1 mole of oxygen reacts with 4 moles of thiosulfate ions, as can be seen in the overall reaction equations. The titration is complete when all of the free iodine has been converted to iodide ions. The endpoint of the titration is determined using a starch indicator, which turns from deep blue to colorless. To perform this experiment, we'll need the following: manganese sulfate monohydrate or dihydrate or tetrahydrate, sodium or potassium hydroxide, sodium or potassium iodide, sodium azide, concentrated sulfuric acid, soluble starch powder, salicylic acid or formaldehyde, sodium thiosulfate crystals, chloroform, potassium dichromate, potassium permanganate, potassium oxalate, 10% dilute sulfuric acid, deionized water, 100 ml beakers, 10 ml beakers, 250 ml beakers, stirring rod, funnel, droppers, 100 ml volumetric flask, 1000 ml volumetric flask, 1 ml pipette, 5 ml pipettes, 10 ml pipettes, 250 ml Erlenmeyer flasks, 1000 ml Erlenmeyer flask, a 100 ml graduated cylinder or a 100 ml volumetric pipette, 500 ml graduated cylinder, 50 or 25 ml burette, a burette stand, 300 ml BOD bottles, pipette bulb or dispenser, weighing scale, spatulas, hot plate or burner, gloves and goggles. To begin the experiment, prepare the necessary reagents and standard solutions required. To prepare manganese sulfate solution, weigh 48 grams of manganese sulfate tetrahydrate or 40 grams of manganese sulfate dihydrate or 36.4 grams of manganese sulfate monohydrate in a 100 ml beaker and add about 50 ml of deionized water. Stir the contents using a stirring rod until the manganese sulfate dissolves completely. Once dissolved, transfer the solution into a 100 ml volumetric flask. Rinse the beaker, stirring rod, and the funnel using small quantities of deionized water and make up the final volume to 100 ml using deionized water. The second reagent is alkaline iodide azide reagent. To prepare this reagent, weigh 50 grams of sodium hydroxide or 70 grams of potassium hydroxide, along with 13.5 grams of sodium iodide or 15 grams of potassium iodide in a 250 ml beaker. Add about 30 ml of deionized water. Stir the contents until they dissolve. Allow the solution to cool down and transfer it into a 100 ml volumetric flask using a funnel. Meanwhile, weigh 1 gram of sodium azide in a small 10 ml beaker and add 4 ml of deionized water using a pipette. Stir the contents to dissolve the salt and add this to the alkaline iodide solution in the volumetric flask. Wash down the funnel, stirring rod, and beaker using small quantities of water and make up the final volume to 100 ml. In the traditional Winkler's method, the final volume is made up to 100 ml without addition of sodium azide. This is the only difference between the traditional Winkler's method and the modified Winkler's azide method. All other aspects, including the testing procedure and the reagents and materials required, are the same for both the methods. The third reagent required is concentrated sulfuric acid. Next is starch solution. To prepare starch indicator solution, weigh 1 gram of soluble starch powder in a small beaker and add about 5 ml of deionized water. Mix the contents to form a paste. Now carefully add this paste to 100 ml of boiling hot deionized water in a 250 ml beaker. You may also add 0.5 grams of salicylic acid or 0.5 ml of formaldehyde as a preservative into the starch solution. I'm using salicylic acid in this video. Stir the contents to dissolve the salicylic acid completely and let the solution cool. The fifth reagent required is a standard sodium thiosulfate titrant solution of 0.0125 normality. To prepare sodium thiosulfate solution, weigh 3.1025 grams of sodium thiosulfate in a 100 ml or 250 ml beaker. Add some amount of deionized water to the beaker. Stir to dissolve the thiosulfate completely. Transfer the contents of the beaker into a 1000 ml volumetric flask using a funnel. Wash down the funnel, stirring rod, and the beaker using deionized water. Make up the final volume to 1000 ml using deionized water. Now, add 0.4 grams of solid sodium hydroxide or 5 ml of chloroform to prevent thiosulfate deterioration. I'm using sodium hydroxide in this video. The sixth reagent required is a standard potassium dichromate for standardization of the thiosulfate solution. To prepare this, weigh 0.613 grams of dry potassium dichromate in a 100 or 250 ml beaker. Add some amount of deionized water and stir to completely dissolve the dichromate salt. Transfer the solution into a 1000 ml volumetric flask using a funnel. Wash down the funnel, the stirring rod, and the beaker using deionized water. Make up the final volume to 1000 ml using deionized water. The strength of this solution is equivalent to 0.0125 normal sodium thiosulfate. The seventh reagent required is crystalline potassium iodide for standardization of the thiosulfate. The eighth reagent required is a dilute 10% aqueous sulfuric acid solution. To prepare this, pipette out 10 ml of concentrated sulfuric acid into a small beaker. Transfer 90 ml of deionized water into a 250 ml beaker. Now slowly and carefully add the sulfuric acid into the deionized water with constant stirring. Allow the solution to cool down. To begin the testing of the water sample for its dissolved oxygen content, we first need to standardize the sodium thiosulfate solution. If it was prepared a few weeks prior to the experiment, the standardization step may be avoided if you're using a freshly prepared thiosulfate solution. Standardization can be done using either sodium biiodate or potassium dichromate. In this video, we'll be following the dichromate method. For the standardization procedure using potassium dichromate, weigh 2 grams of potassium iodide in a small beaker and introduce it into a 1000 ml Erlenmeyer flask. Wash it down and dissolve it in about 150 ml of deionized water. Add to this 10 ml of 10% dilute sulfuric acid using a 10 ml pipette. Now, using a 10 ml or a 20 ml pipette, introduce exactly 20 ml of standard potassium dichromate into the flask. Place the flask in the dark for about 5 minutes. Now, add about 220 ml of deionized water to make up the final volume to 400 ml. Meanwhile, fix the burette on the burette stand and fill it with standard thiosulfate solution prepared previously. Adjust the level of the lower meniscus to the 0 mark. Now, titrate the dichromate solution in the flask with the thiosulfate solution in the burette dropwise till the solution in the flask becomes pale yellow. Now, add about 5 drops of the starch indicator solution to the flask. A blue color is produced. Continue adding the thiosulfate dropwise into the flask until the first disappearance of the blue color. If exactly 20 ml of the thiosulfate in the burette was used up to bring about the titration endpoint, it means that the thiosulfate is indeed of exactly 0.0125 normal concentration. Consumed values of more or less than 20 ml means that the normality of the thiosulfate is less or more than 0.0125 normal respectively. In such cases, the titer values in the DO estimation should be multiplied by the correction factor n/20 in order to compensate for the difference in the normality of the standard thiosulfate used. Once the sodium thiosulfate has been standardized, we can proceed with the DO estimation of the water sample. We begin this by first collecting the water sample from the source using a special container called the BOD bottle. Each bottle has a unique serial number printed on the bottle in order to avoid sample mix-up when collecting numerous samples from different sources. Details on the sample may be entered against the same serial number in a collection registry book in the field. The BOD bottle has a wide conical mouth and a tight-fitting ground glass stopper with a pointed lower tip. These are unique design features of the bottle to avoid the trapping of any air bubbles in collecting the water samples, and also to minimize contact between the sample inside the bottle and the atmosphere outside. To collect the water sample, take a BOD bottle with intact stopper and immerse it to the desired depth in the water source. Now carefully remove the glass stopper from the bottle and allow the water to seep into the bottle. Close the bottle once it's completely filled with the water. Make sure no air bubbles are trapped in the bottle. The next step, also known as oxygen fixation step, may be performed in the lab or in the field itself. The fixation step is where the dissolved oxygen content of the water sample is converted into a more stable oxide precipitate of manganese. To perform the fixation step, carefully remove the stopper from the bottle and add 1 ml of manganese sulfate solution to the water sample using a 1 ml pipette. Using a second pipette, add 1 ml of alkaline iodide azide reagent to the sample. Make sure that the pipette tips are immersed well below the water surface in the bottle when adding the reagents. Now carefully stopper the bottle, taking care not to introduce any air bubbles. You will observe a brownish precipitate of manganic hydroxide begin to form in the bottle after addition of the reagents. The intensity of the brown color is directly proportional to the dissolved oxygen content in the water sample. Now pour off the excess water sample which was displaced from the bottle during the addition of the reagents into a small waste beaker. Thoroughly mix the reagents with the water sample by vigorously inverting the bottle several times. Allow the precipitate to settle down. At this point, the oxygen content of the water sample has been fixed into a more stable form. If circumstances do not permit proceeding to the next step of testing the water sample, maybe because you are still in the field collecting other samples, or a lab setting is far from your location, etc., you may store the bottle in a cool, dark place for up to 8 hours and proceed to the next step once the situation permits. However, it is always advisable as far as possible that you proceed immediately to the next step without delay. At this point, before you proceed to the next step of testing, fill the burette up to the 0 mark with the standard sodium thiosulfate solution using a funnel. Keep this aside and proceed to the next step of testing. Using a 1 ml pipette, carefully add 1 ml of concentrated sulfuric acid by letting it flow down along the neck of the bottle. Make sure the pipette tip is immersed just beneath the water surface. Now carefully stopper the bottle again. Pour off excess displaced water sample into the waste beaker and dissolve the precipitate by vigorously inverting the bottle several times. Using a 100 ml pipette or a 100 ml graduated cylinder, take 100 ml of the sample and introduce it into a 250 or 500 ml Erlenmeyer flask. Now titrate the sample using the standard thiosulfate solution in the burette. Run the thiosulfate dropwise from the burette till the brown color of the sample in the flask becomes pale yellow or straw yellow. Now add 3 to 5 drops of starch indicator solution to the sample and mix well. The sample now turns blue. Immediately continue the titration until the first disappearance of the blue color on the addition of a single drop of thiosulfate to the sample. Repeat the titration about 3 times using fresh 100 ml samples taken in fresh Erlenmeyer flasks. Calculation. When 100 ml of the sample is titrated using 0.0125 normal or N/80 sodium thiosulfate, every ml of the thiosulfate used up in the titration is equivalent to 1 mg of oxygen per liter. The sample volume and the concentration of sodium thiosulfate used can vary in different textbooks. However, it's just a matter of making proportionate adjustments in sample volume and standard thiosulfate concentration based on the above statement. The radial Stewart modification of Winkler's method, or the permanganate method. This modified Winkler's method is suitable when appreciable quantities of iron salts, organic compounds, and nitrites are suspected to be present in the water sample to be tested. It is highly advisable to follow this method as a general rule when testing water samples of unknown quality. All the reagents required for this method are the same as described in the Winkler's method. However, 2 additional reagents are also required. These are potassium permanganate solution, which is prepared by dissolving 6.32 grams of potassium permanganate in 1 liter of deionized water. Potassium oxalate solution, prepared by dissolving 2 grams of the salt in 100 ml of deionized water. This solution is quite unstable and therefore has to be prepared afresh for each test. To begin the procedure, collect water sample as described before in a 300 ml BOD bottle. Add 0.84 ml of concentrated sulfuric acid to the sample. Immediately add 1 ml of potassium permanganate using a second pipette. Mix well by inverting the bottle several times and leave aside for at least 20 minutes. The typical violet color of permanganate should persist for at least 20 minutes. If not, add a small quantity of permanganate solution. Mix well by inversion. Repeat the addition of permanganate until the color persists for at least 20 minutes. Now add 0.5 ml of potassium oxalate solution and mix well. Set aside undisturbed for about 5 minutes. If the color of the permanganate persists after addition of oxalate solution, add another 0.5 ml of oxalate solution and mix well. When the permanganate color has disappeared completely, add 1 ml of manganese sulfate followed by 3 ml of alkaline iodide azide reagent. Mix well by inversion. Allow the precipitate form to settle down, and add 1 ml of concentrated sulfuric acid along the neck of the bottle. Mix well until precipitate dissolves completely. Take 100 ml of the sample in a flask and titrate with 0.0125 normal sodium thiosulfate until the brown color of the sample becomes pale yellow. Add a few drops of starch indicator and continue titrating the sample until the first complete disappearance of the blue color. Each ml of thiosulfate used in the titration corresponds to 1 mg per liter of dissolved oxygen in the sample.